Welcome to the final session of the Meet the Fellows event. So we have 3 talks in this session by fellows in the Graph Limits and Processes on Networks program. And the first talk is by Yeganeh, who will tell us about local algorithms to predict network activities.
Thank you. My name is Yeganeh. I'm a PhD student at Stanford, advised by Amin Saberi. Today, I'm going to talk about epidemics on network. The first part is going to be the 5-minute version of the longer talk I gave last week. Then I get to more empirical work. So we have an infection spreading over a network like COVID, for example, and the properties of this network matters on how the infection is going to spread. For example, if we have isolated sets of families, if one of them get infected randomly from travel, there is no risk for the others. But on the other hand, if we have a party-goer family, if they get infected, there is a chance of leading to an outbreak. The main question we are asking is that what kind of information about the network do we need to predict an outbreak? And this question has been traditionally answered mostly with a modeling perspective. So there are 2 steps in the more traditional ways to answer this question. First is to choose a network model to see how the interaction between people goes. For example, there are many of these models: Erdős-Rényi, configuration model, stochastic block model, etc. And you choose one of these models as you desire, then you have to estimate the relevant model parameters. So for example, if you chose Erdős-Rényi, you have to estimate what's the average degree. And if you chose configuration model, you have to estimate what's the degree sequence. But the question is that we don't know what's the right model. And can we have a model-free way of estimation of epidemics? To answer this question, we are considering a very simple epidemic model, which we have a network of individuals or the nodes, edgeable interaction. Initially, one node uniformly at random is infected. They transmit the disease independently to their neighbors with fixed probability P. And after that, they recover and they're immune to reinfection. So one node is infected, they transmit the disease. The same happened with the new infected node until everybody tried their chance. This is equivalent to SIR model with constant recovery time. And the main thing we are interested here is an outbreak, the event of an outbreak, where super constant number of nodes are getting infected. Now, going back to our question, which was how we can estimate epidemic without knowing the model, we propose a simple algorithm for that. It's a local algorithm to predict epidemics. This algorithm has information about the network. We don't know the network, but through this oracle, we are learning something about it. So the algorithm gets K as an input, and it first draws a uniform random node and assume that node is the first infected patient. And starting from that node, it sees if it can infect K other people in one run of simulation. So here for K equal to 4, we see it infects one neighbor, that neighbor infects another one, but the infection dies out. So in this run of the scenario, the answer of the algorithm would be 0, there was an infection of size 4. And a simple estimator using this algorithm would be just take average over a few queries that you get. Now, the question is, how many queries do I need? And in our work with Christian and Amin, we showed that if we have a convergent sequence of well-connected networks or some sort of big expanders, then to get a 1 minus epsilon approximation of the epidemic size and the epidemic probability, I only need constant queries with K equal to a constant as an input. And the second part of the theorem, we showed that the final size of an infection is either a constant or a linear size in terms of the network. So there is no in-between situation. A few notes about the algorithm, that theorem I showed you recovers many of the previous results on different network models without assuming them. So for example, configuration model, preferential attachment, and household models. The second thing is that the algorithm has some nice properties. For example, it can be implemented in constant time. It's model-free, and it preserves edge differential privacy, and it's extendable to dynamic models when nodes come and go. And it doesn't require anything like local tree, like a structure that some of the previous model imposed on the graph. And the main technical thing that we used was graph limit, which we saw a lot of nice introduction by Christian and Jennifer last week. So the second part of the talk, I'm going to focus on the application of studying of epidemics on networks in real life. And their application is on school reopening. This is a collaboration with a bunch of nice privates at Stanford, and we work with Los Angeles School District since fall 2020 on this. A brief background about Los Angeles School District. They are the second largest school district in the US with 700,000 students. And they have a large population of underprivileged students that they really needed to go to school because of education and also getting even free meal. And back in 2020, when all the schools were closed, one of the main challenges they had was that what's the right policy to implement so that we can safely keep students back to school. And for answering that question, we need to first identify how we can quantify risk here. And the more traditional way about risk is looking at the absolute number, absolute risk. Meaning that, for example, in 2021, California guideline says that if the case rate of the community are below 25 per 100K, then the school can be open. So this is just the absolute number, which is very sensitive to maybe a lot of noise that we have from COVID cases. Some areas have good testing, so inherently the case that the report is higher. But are they really schools not safe to reopen? So instead, we are taking a relative risk approach. We compare the risk that if the students go to school with the case that they don't go to a school and they get the infection from community, like going to grocery store or like playgrounds. And to identify that relative risk, there are two important factors. First is the inbound rate, which is the rate that the students are getting infected from the community. The second is the within school spread, which is the rate that the students would get the infection by going to school. And we say schools are safer to reopen if students in school spread is lower than the inbound rate from the community. So the inbound rate can be estimated from community prevalence and taking care of how many cases are in different age groups. But the in-school spread, to estimate that, we are using the network model. And here I'm showing you a hypothetical school network where nodes are either teachers or students, and there are a hierarchy between how students would interact. The higher level is the whole school, then we have grades and cohorts, and we can have different levels of interaction, which are shown with different colors here. And then there is also the community inbound rate that students and teachers are getting infected from the whole community. And I'm hiding a lot of details here, but with different parameter settings that we set, both for the number of edges that we can have and the strength of them, we can now compare the community inbound rate with how the school, how the infection is spreading within the school. And here I'm showing you some qualitative results. And so look here in this table, different rows, different blocks of rows shows different 7-day average cases in the community. And we are bundling these different countermeasures that can be implemented in school, from low, medium, high, for example, how much they're using masking, how much they're social distancing or not. And we are looking at 3 different testing scenarios. So whether they're getting, all the students are getting tested every 3 days, every week, or bi-weekly. And as we see here, in 3-day testing and 7-day testing, school in a spread rate is lower than the community most of the time. And when we get to bi-weekly testing, and then they are mostly not safe, except when the community rates are higher. And the intuition is that if the community rates are so high, then 14-day testing is keeping some students safer from getting infected from their classmates. And actually, LAUSD school reopened in August 2021 with weekly testing. And they had very few outbreaks before January Omicron, so they didn't have really much infected. It worked well until then. And with that, I thank you so much. I stop here and I'd be happy to take questions.
Yeah, let me pass.
Thank you for the very interesting talk. I have two questions. First one is on the dynamics, where on the first part, it seems like the agents are trying to, the transmission, explore the link once and then don't transmit. So, but if the transmission is not successful, so the second node is not immune. So it seems there could be also a second chance for the transmission.
Yeah,
I was wondering if you can comment on that.
You can adjust it with like how you change P, maybe. It's the same. You can think of like their interaction of nodes be modeled with like some Poisson random process, and then if the infection rate, if the infection time is fixed, then it will be equivalent to just finding some P. It's the same as that. Like, so if the Poisson process has happened twice, then it doesn't matter for me. It's just the first time they get transmitted to the disease.
My second very quick question is: the weekly testing is shown to be better. Does that relate to how the incubation period for COVID, which roughly 2 weeks, or it's?
Yeah, that's a very good question. So this here we are using the earlier variants of COVID, where like the incubation period was longer, and I'm pretty sure if you do the same analysis for Omicron, this like weekly testing wouldn't be as good as this year, because the incubation period are shorter and you need like more frequent tests to like get rid of the outbreaks.
The next speaker can set up.
Thank you, Jen, for the interesting talk. Just can you tell us how actually you create the last table? I mean, how did you measure the safety? And you say it is safety. Also, how did you find out the cohorts or all of that in the real practice in the school? Thank you.
That's a great question. So about the cohort size and the school specific parameters, we talked a lot with teachers and principals. So like based on if the school is like for high school, elementary school, we changed the
So you went
parameters.
To the teacher and you asked them,
Like,
those students are friends and they...
No, not the, oh, you mean the interaction. So like about the cohort size and school size as we use teachers data, but then about the ages, then we assume like, we did since a sensitivity analysis between like different levels of interaction that they can have. Like then at the end of the day, with different parameters, we like draw some hierarchical statics, stochastic block model.
So you asked it?
Sorry, can you say? And the ages, no, but just about like physical characteristic of the school, like how large is the classroom, or like those questions were like, yeah.
And what was the final meaning of the safer? Why the school was safer than community?
What was the meaning of safer? Means that the within a school spread is lower than the community.
I see.
So a question, so like all those apps that you were doing, you're getting information, about phones being close to each other.
No.
Is there any way to access that, to get that information?
For school, I don't think. I don't know of any mobility data. For general public, yeah. There are some mobility network data available. I think SafeGraph is the main like company that like sells those data. SafeGraph, yeah.
They have the data from wherever.
Yeah, from GPS data, and that. But even in those data, most of the data is like people above 18. It's not for kids.
Above 18.
And above 18, I mean their age. So
18,
it's like 18, 1 8. Yeah.
And your parents don't like.
No, not the children. I'm asking whether you can get the same questions. You could ask the same questions about public experts, right?
Yeah.
And then you have probably closer information, more refined information.
Right. There are ways to answer that question, and there are some publications. I'm studying some like others for like general population, like vaccination, but I'd be happy to check that.
To universities, right?
Universities are
safer to keep your university open or not?
Yeah.
And then you could use mobile data in university, people opt in or something.
Rules invasion of privacy, but
That's why I said opt in.
right.
What do you mean invasion? If you decide not to
If
do
you
what
opt
you
in,
want.
yes.
What?
No, if you opt in, right.
Maybe you could do the choice of privacy on these networks. I mean, they have these notions of two graphs that are, let's say, one edge apart from each other, and the fact that you know or don't know if the edge participating.
Don't ever place a heavy one that shut up the electrons institute, and that's the next person.
I don't have to do that terminology.
Okay, so yeah, lots of interesting discussion. Yeah, we'll have opportunities to do it offline. Let's continue with the